Among both beginning researchers and experts, the most common way to ruin an otherwise perfectly good study is by small errors made at the design phase, long before the data is even collected. Fortunately, this can also be the easiest to avoid. My name is Jeffrey Frank. I'm a statistician and the CEO of Stat59. In this video, you are going to learn about 10 mistakes that researchers make at the design phase and some simple solutions on how to avoid them.
The objectives of this lesson is to learn about 10 things that can ruin your research study before you even start. These are mistakes that researchers of all abilities make at the study design phase that can be difficult or even impossible to correct later on. And we will learn how to use common sense and some simple statistical principles to avoid them. Number 1, chase a problem. The best research papers investigate a single solution to a single problem. These studies are easy to design. They have a single statistical hypothesis. It's easy to collect the data, easy to analyze the data, easy to write up the report, and easy for the reader to understand. In one of my favorite books called The Idea Factory, the authors talk about the fact that there are plenty of good ideas out there, almost too many. What is really hard to find is a good problem. Make sure from the outset that your study is chasing a problem. A good research topic is not studying sales of ice cream at an ice cream store. A good study would be to chase a problem. How do we increase sales of ice cream at our gelateria? Number 2, have a single hypothesis. It is not only important, but really it's mandatory that any studies that are using statistics to analyze their data have a hypothesis. And in this wonderful article that's a little bit verbose and a little bit lengthy, but suggests excellent ideas for statistical reporting, it states that statistical theory really requires that the hypotheses are developed before the data are examined. This is super important. What is a hypothesis? Well, a hypothesis is a claim or assertion about a value of a single parameter, the value of several parameters, or the form of a probability distribution. That's all fine from the statistical point of view, but what does that mean for us? It means we should have a thought about what we're looking for before we start collecting data. Again, going back to my gelateria, a good hypothesis about ice cream might be, my hypothesis is that adding anchovies and gorgonzola cheese to the chocolate ice cream will increase the ice cream sales. Starting a study with that single hypothesis makes for a very elegant and well-designed study. Now, I do a lot of research in disaster medicine, and we do a lot of qualitative studies. So what about qualitative studies? Well, qualitative studies may not have the statistics behind them, but they still need a hypothesis or at least a central question. And in an excellent book by Cresswell, he states, we recommend that a researcher reduce his or her entire study into a single overarching central question. And examples of these questions might be, what is the lived experience of loss for victims of earthquakes? Or what relational process theory describes the effects of previous occupation on post-earthquake recovery? So whether you're doing a quantitative or a qualitative study, the best studies start with a single hypothesis that is formed before the data is collected. Number 3, use a validated tool. One of the things that many researchers want to do is they want to measure something. This could be performance on a test, or stress in environment, or satisfaction with your ice cream. Unfortunately, it is very difficult to develop a new tool, a new measurement instrument, and use it in the same study. And here I will often say to the researchers I work with, use your librarian, get an adequate literature search, and look out there for a previously validated tool. In an excellent article a study performed by one of the master's students at the master's degree where I work, we came up with this issue. So a panel of 12 physicians have written extensively on the subject was created to determine inter-rater reliability of a 10-question quiz. And you see that what happened is the quiz showed a kappa value of 0.06, which means that the experts themselves could not agree on the correct answers to the quiz, which means the tool failed the validation phase. Now you can go on and use these in these tools that have not previously been validated, but you will often find, as did this experimenter, that you were unable to pick up any difference. And in the end, in this study, the examiner found that the confidence interval for the 95% certainty showed that the overall score between groups changed by less than 1.5 out of 10. So what's the issue here? Well, this study tried to develop a new tool, this new 10-question quiz, and use it to evaluate the efficiency of a teaching instrument. And doing those two things in one study is almost universally a recipe for disaster. So find that validated tool. Number 4, aim for tall and skinny. One of the things that beginning researchers often want to do is to take some sort of phenomena and look at all the different parameters in it. This will often take place for instance, in questionnaire or survey design, where the survey asks 200 questions out of their participants. These are not good data sets. So this is an example of a relatively bad looking data set. You see it only has 6 rows. So in this case, we've taken 13 measurements from 6 different individuals. Well, these are very, very hard to analyze. And they have a very low power, and they're very, very likely to get negative results. So usually we like to aim for at least 10 to 20 observations per factor analyzed for reasonable power. So you can see here with 13 factors analyzed, we really need between 130 and 260 observations to get useful data. What's a better way around this? This is called the curse of dimensionality. And we statisticians love to talk about this. It's a mathematical solution in multidimensional space. What does it mean in practical means? It means that we should aim for tall, skinny data sets. What does a tall, skinny data set look like? Well, that would be a data set, for instance, where you interviewed 100 people, sent a survey to 100 people, but asked each of them 5 questions. That would be an excellent data set. Or in the case of my ice cream, we would need to ask maybe several questions about the ice cream. Maybe did you like the flavor of the ice cream? Did you like the consistency of the ice cream? Would you buy the ice cream again? And administer that survey to many people. So aiming for that tall, skinny data set, asking focused questions, getting focused data from a large number of observations. Check your sample size. Now, sample size is a chaos field for everyone. This is a terrible issue for researchers, and it can be a super hard issue even for us as statisticians. On the left, you see the chaos field, which is what I feel every time I move into sample size. And on the right, you see the textbook, which is about 400 pages that shows various ways of determining sample size and power for various studies. Why do I show you this slide? Remember that getting your sample size is not easy. This is not a trivial problem. How do we select a sample size? Well, the first thing is really to just make it as big as you can get. Sometimes this is the whole population. So if, for instance, you are doing a research study on a teaching intervention for all of the residents at your program who are doing disaster medicine, we would like to apply the teaching intervention to the entire population, all the residents at our site. In this case, there's no need to do a sample size calculation because the sample size is fixed. It is preset. If you don't know where to start, sometimes you don't have any idea where to start, 30 is a nice place to start for pilot studies. And then finally, there's the type of power calculation. And there's several ways to do this. Often we see calculators online that use sort of a generic effect size and give not particularly accurate results, and it's questionable whether they're helpful. And then the other way is by using the variance and the mean of a target population. I want to run through quickly on the steps that you need to find a sample size with power calculations, only so that you can understand how difficult this is. So first of all, you need to have your hypothesis fully formed before you can even write your sample size calculation. You also need to know exactly which statistical test you will use to analyze the data. You're going to have to know your alpha level. This is at what p-value you will think that it's significant. You need to specify an effect size, and effect size is not trivial to obtain. Usually you need historical values of your mu and your sigma, historical values of your average and standard deviation. Then you specify your target power and calculate it. The thing to understand here is that sample size calculation is not trivial. If you were doing any type of study that involves a danger to your participants, perhaps you're testing a new drug on your participants, and it will require sample size calculation, make sure you get help very early. As you can see, it requires a number of decision points be made before you can calculate the sample size. Get help on this. Number 6, avoid or correct for multiplicity. So here's my gelato experiment again. At this point, we have a fictitious experiment where we added our gorgonzola and anchovy additive to 20 different flavors of coffee, and then, or 20 different flavors of ice cream. We then tested them out to see if there was a difference between with or without the additive. And we see that we used a t-test with an alpha value of 0.05, and we found that in 3 cases there was a difference between the two. So who's done this before? Many of us are victims of this, and I admit to early on my career in research that fortunately nobody agreed to publish, I used this exact technique of applying 20 different t-tests to a data set. What's the problem? Well, the problem here is with multiplicity. So we are using an alpha value of 0.05, which we believe means there's a very small chance that we will accidentally reject the null hypothesis. Unfortunately, when you do 20 of those studies, your alpha value actually becomes quite big. And in fact, if you do 20 t-tests on this data, there's actually a 64% chance of making one or more rejections, simply by chance. Okay, so we absolutely cannot do this. What's the solution? Well, there are a number of different statistical ways to avoid or correct for multiplicity. The first way is just by using common sense. Do not design a study like this. This is a study here that clearly lacks a focus, clearly lacks a single hypothesis. If you are going to be using techniques that involve a number of different hypothesis tests, then we need to use statistical methods to do that. And those can be such things as Bonferroni corrections or ANOVA. If you're going to be doing this, make sure that you get statistical help at the outset to make sure that this is addressed in the initial study design. Tabulate wisely. This is one of the ways that researchers waste hours and hours of their time. So this, as you can see, is a beautiful tabulation on a spreadsheet of an experiment that I did with a student on triage. And you can see the student has at the top of the spreadsheet given all the results, and then a bunch of summaries, including the range and the mean. These are all completely useless to statisticians. As statisticians, we want to get our data in a simple table and input it into our statistics software. And unfortunately for this student, I had to send the student back and say, this is not a useful way to tabulate your data. In fact, I need the data to look like this. And generally, statistics software requires very simple data tabulation. It'll usually be a single sheet on a spreadsheet with each row being an observation. The important thing here is to tabulate with the data analysis in mind and to communicate early with the analyst. Without really understanding how you're going to analyze the data, it's almost impossible to tabulate it in a useful manner. And we have other videos on our YouTube channel showing you how to tabulate if you want to know this in more detail. The thing that saves most researchers the most time is communicating early with the statistician. Number 8, include the outliers. It's very tempting when we do our studies to look very closely at any types of values that seem that they just don't fit. We can see them sometimes plotting them. As you see in this plot, there's clearly one data point that does not seem to fit. What do we do with these? It's particularly common if researchers look at these and feel that the data point that they're seeing does not agree with what they think should have happened, to simply exclude these outliers. But we can't, and that's very important. So what do we do when we find a data point that looks clearly like it doesn't belong? Well, the first thing is to check for clerical errors. So here we back up and look, did someone write something down incorrectly? The second is to look, there are statistical methods to ask, is this really an outlier? We can then repeat the analysis with and without the outlier, but you cannot just remove them. So this is very important when you're performing your study, early on in your study, when you're gathering your data. Getting a data point that looks like it does not belong is not justification for avoiding it. Include it in your analysis. Work through with your statistics plan to address them properly. Number 9, don't be a p-value hacker. In this wonderful article called Fooling Ourselves, which looks deep down at some of the basic principles of statistics, they come up with a number of names for this that includes data dredging, p-value hacking, data snooping, harking or hypothesizing after the results are known, or jarking, justifying after results are known. And this is common among beginning researchers who tend to work through their data by first collecting a huge amount of data, second, looking through the data to see if they find any trends, and third, assaulting the data with a number of statistical tests until something comes back positive. This is absolutely not appropriate and is not how statistics work. In fact, you'll see that there's a lot of controversy about p-values right now. Much of the controversy is not due to the intrinsic mathematical problems with p-values, but the way we use them. Why is this? Well, as this article states, the problem is that post hoc stories can be concocted to justify anything and everything, and so end up truly explaining nothing. What is the biggest step towards not being a p-value hacker? That's right from the beginning, having a simple problem that you're addressing and having a single hypothesis. P-values and confidence intervals must be pre-planned and should be used only for your initial research hypotheses. If you do exploratory data analysis, looking through the data afterwards, and you find unusual findings or trends, these are absolutely appropriate to add to your paper. However, they must be labeled during your study. So it's okay to talk about them. I found the following interesting anecdotal discovery while I was analyzing my ice cream data, but it should not be hacked through to a p-value. And finally, to finish up, number 10 is just ask for help. Remember that everybody's a genius, but if you judge a fish by its ability to climb a tree, it will live its whole life believing it is stupid. For many of us doing our research projects, we are not expected to be statisticians. We are expected to be able to develop a research problem and to develop a research plan. You are not on your own out there. Ask for help with your statistics plan. And as we saw with all 10 of these factors, the most important thing is asking for help at outset during the planning phase of the study to stay out of trouble with statistics.
In this video, we saw that there are 10 simple things that we can do at the study design phase to pave the way for a guaranteed research success. My name is Jeffrey Franck. I'm a statistician and the CEO of Stat59. If you'd like to see how the Stat59 web app can help you design your study and pave the way for success, please come visit our website at www.stat59.com.